Guy, you can see me, guys, with a Humber uniform, and this is my new room. And I'm going. There are many questions that people of dynamics ask, so I'm just going to say you two small things. I'm going to bring an example that Mohammed sent me, and the other one that Lekrai sent me. First of all, I'm going to talk, and probably you know, about so-called Dalambert's principle. Together we did statics. And the equation of statics, you remember, was sum of the forces, sum of the moments. So we said that the total force of the system was 0. And we divided in the component x, y, z. And we said that the total moment of the systems were 0. This was in statics. Now you are in dynamics. In dynamics, things move. So because move, when according to the second law of Newton, when I have a total force, it's going to cause an acceleration. So it's going to be like this. Sum of the forces equal mass times acceleration, or sum of the moments. When we have moment, instead of mass, I have the moment of inertia. Instead of acceleration, I have angular acceleration. So this is the second law of Newton. Now, let me bring this one here. It's going to be like this. Sum of the forces minus mass times acceleration equals 0. And sum of the moments minus moment of inertia times angular acceleration is 0. You see, those equations are almost the same. You know what does it mean? If you have a problem of dynamics, guys, you know what you do? You treat it like the problem of statics, but on top of all the forces that you have in the system, you have to add this force, which is called inertial force with the sign minus. Once again, so you have a system of forces. On top of those system of forces, you have to add the inertia force, which is mass times acceleration. If you add this one, you can treat every problem of dynamics as it was a problem of statics. Remember last year I said that we're going to need statics even in dynamics. So all the system of forces, plus the forces of inertia, but with a reverse sign, and that's it you have to do. I'm going to see the example that Lekrai has. I don't remember the numbers, but probably many of you had, and how I'm going to apply the principle, the Dalambert principle. So he had a plan, and was given the angle, if I'm not wrong, is 37 degrees, but doesn't matter. Was given the mass of an object, was given the mass, I think was 30 kilograms, and this angle was 27 degrees. It was given the coefficient of friction between those two surfaces, which is 0.3, and was asked how much is the force that you have to push here to cause the acceleration 3 meters per second square. So how much is the pushing force? Now, all we have to do is to put the system of forces. Please follow me, guys. What we have here? We have, first I have the weight. This is the weight. How much is the weight? Is mass, which is given, times gravity. What else do I have? So this weight has two components, guys. This is this component. If this angle is 37 degrees, this angle is 37 degrees too. So this component here is weight cosinus 37. And this other component here, the component on the parallel with the surface, is weight sinus 37. We know everything We know those components. This one, remember what name we gave him? Normal force. So how much is the normal force? Weight cosinus 37. Now, as I said, the body is moving up because of this force, push force that was asked. We don't know this force. That's what is asked, to find this force. And this causing us an acceleration. This causing this one, mass time acceleration. Okay? What else we forgot? The friction. The friction between those two areas. The forces of friction, as you know, are normal force times the coefficient of friction. Normal force, you have it. Coefficient of friction is given. Now, what is the direction? Never forget that. The force of friction is always opposite the motion. So the force of friction is this one here. So now, what I have here? I have the push force, I have this, this, and this. How do I write the equation of statics? I'm going to say it. What I have? All this push force. So I'm going to say push force, which we don't know, minus forces of friction, minus this component, W sinus 37. Now, this force I'm going to add with the reverse. Minus mass time acceleration equals 0. This is an equation of statics, which the only thing I don't know is that Muhammad was given a platform. I think the angle was 60 degrees, and this one was 3,000 pounds. So if it gives them 3,000 pounds, is given the weight, and was given the coefficient of friction, I think was 0.2. Was given the coefficient of friction as 0.2, and was asked the component, the total component of the forces that pull this one down. The total component of forces that pull this one down. What forces we have? Again, we have the weight. The weight has this vertical component, which is weight. This is weight cosinus 60. In this case, cosinus 60 is 0.5. So this is weight times 0.5. And we have this component here. I don't remember the numbers, how it was, but this is weight sinus 60. So this is the component pushing down, weight sinus 60. But hold on a minute. What we have here? We have the forces of friction. Now you see the forces of friction are directly on the other way. Why? Because are opposite the motion. The motion is going down now, before it was going up. So the total force here is going to be this minus this. So the total force pushing down is going to be weight sinus 60 minus, how much is the force of friction? Coefficient of friction times the normal force. So this is the normal force. This is the normal force. So it's weight cosinus 60. That's it. That's it. This is the exercise. I guess you understand that. Thank you. Bye-bye. And I miss everybody. If I had the chance to have you again in class, I would let you use the cell phones as much as you wanted to.